Our next speaker is Dr. Sameer Singh. So Dr. Sameer Singh is an associate professor of computer science at University of California, Irvine, and an Allen AI fellow at Allen Institute of AI. He is working primarily on robustness and interpretability of machine learning algorithms, along with the models that reason with text and structure for NLP. Sameer was a postdoctoral researcher at University of Washington and received his PhD from University of Massachusetts. He has received the NSF Career Award, selected as a DARPA Riser, UCI Distinguished Early Career Faculty Award, and Hellman Faculty Fellowship. His group has received funding from Allen Institute of AI, Amazon, NSF, DARPA, Adobe Research, Hasso-Plattner Institute, NEC, Base 11, and FICO. Sameer has published extensively at machine learning and NLP venues and received conference paper awards at KDD 16, ACL 2018, AMNLP 2019, AKBC 2020, and ACL 2020. So today he will be talking about like evaluating and testing natural language processing models. Yeah, over to you, Sameer.
Thank you. And I assume you can hear me fine?
Yes.
Awesome. Thank you. So today I'm going to be talking about evaluating and testing NLP models, and a lot of what I'm going to talk about goes beyond just NLP. So hopefully people who are experts in other domains can take some of these ideas and think about what it means for what they work on. Okay. So let me give you sort of a introduction to where NLP is and why I wanted to work in this specific area. Right. So think about this problem of working with a model and trying to figure out whether it really works or not, right? So suppose you're a researcher, you're working on your computer, and you have a nice model that you're pretty happy with. You've been training it, taking care of it, growing it, and you like it a lot. And then suddenly a new model comes out. Everybody's tweeting about this. Everybody says that's the new best thing, called Oscar in this case. And that's just supposed to be better than what you're supposed to be doing. And so the natural question that comes up is that, is this Oscar thing any better than my existing model, right? Like, is there anything more interesting in this model than what I have already, right? And Facebook, all of these places are also looking at these new models coming out and asking, hey, should we replace whatever we're using right now, underlying our NLP model, with this new thing that has come out. Right? So let's actually think about how it is evaluated right now, this question of how models really work. One popular way is to pick a task and just measure accuracy on the task, right? So let's say we pick question answering and we say like, okay, if this model is good, if it comes close to humans, then it must be good. And so that was the idea with one of the most popular leaderboards for this task called Squad. This is Stanford question answering dataset. It came out in 2016, and it took about 3 or 3.5 years to essentially get a model to be better than humans on that task, right? Which kind of makes the leaderboard a little less useful, because you have something that's better than humans, it's not worth competing on that task. Right? They came up with a different leaderboard called Squad 2.0, and you can see in this Squad 2.0 as well. It came out in 2018 sometime. By 2019, it took an year and a half. The models were better than humans again. Okay. So maybe question answering, at least the way these guys phrased it, maybe that's not the right thing to be measuring your performance on. If you want to see how good you should be looking at the performance, maybe you should be looking at the performance on a bunch of different tasks. That was the idea behind the Glue leaderboard, which contained many different tasks. So you can see certainly this screen is full of numbers. That's because there are lots of tasks, which are columns here, where the models are being evaluated on. And you can see in the ranked list here, humans are at number 9. And this is a pretty old screenshot. Humans are much worse on this task. So again, it kind of loses its purpose. Like the models are competing on being better than humans. It's kind of meaningless at that point. They had a sequel called Superglue, which had a bunch of even more difficult tasks. And it took a little bit longer, but even on that leaderboard, I think earlier this year, it's been almost a year, I think, the numbers are now better than humans again. And this is a pretty old screenshot, but the humans are at number 3. And all these other models seem to be better at that. So one conclusion after looking at all of these things is, why do we need these new models? Why do we need to be trying to get better at NLP? It's pretty clear we should just be patting ourselves on the back and congratulate ourselves because we have solved NLP. Now, if you followed machine learning and if you know what I work on, these are the kind of questions that this is clearly not the case, right? We are far from solving NLP. There are lots of problems with these models. I'm going to give you a few examples of some of them. The first one is that there are lots of shortcuts in these models where it gets the things right for completely wrong reasons. So here's a quick example where there's an image and a question being asked of the image. So there's NLP, but there's also vision going on here. What is the mustache made of? The model is supposed to look at that question, understand what's going on here, understand that mustaches are this conceptual thing here, doesn't necessarily mean hair. In this case, it's banana, and it's able to give the answer banana, even though it has never seen such a mustache, and I'm sure most of you have never seen such a mustache in real world. And it seems really cool. The model is able to answer it. That's why it's better than humans. It's really accurate. And so, yeah, I think this is cool. What's the problem? The problem is if you ask it a different question, what are the eyes made of? The model says bananas. Again, this is really weird because we have completely changed the question. The answer is clearly not bananas, but the model seems to be saying the same thing. You can say what is, and it says banana. You can say what, and it says banana. Somehow it's focusing on pretty much any question that is asking about what's the object in this image. It seems to be saying banana, and it looks accurate because the benchmark doesn't somehow ask these different questions. They only ask the first question. Right? Here's another example. This one is a little bit more realistic and maybe a little bit more dangerous in some sense. This is sensitivity to phrasing. So you could have another image. This is a little bit more realistic. You're walking around in a foreign country and you see a stop sign, and let's assume you don't know what that means. You can say, hey, what type of road sign is shown? You can take a photo and the model is able to say stop and everything's great, right? But it turns out that instead of what type of road sign is shown, if you instead say which type of road sign is shown, which is essentially the same question, these two questions should give you the same answer. Turns out the model says do not enter. It's the same question you're asking it slightly differently. It has changed its answer. Here's another example. This is an example of question answering from a piece of text. So the kind of thing you would do web search over. So, for example, you might want to know how long is the Rhine River? And these question answering systems look at the paragraphs, figure out, okay, this information is kind of spread out over multiple sentences, but they're able to figure out that 1230 kilometers is how long Rhine is. But if you ask a slightly different question, which is essentially the same question, except that you add an extra question mark. It's not even a typo. It's just you really, really care about the answer. There's no reason for the model to give a different answer, but it does. It says more than 1 million. And so clearly there is a mismatch here. These models are not the complete solution for sure, but the leaderboards seem to suggest that they are, right? So what's kind of going on here? Essentially, I think there's a lot of problem with these accuracy and leaderboards where things look very different from what they actually are. One of the biggest problems is that the leaderboards essentially duplicate the biases. If there is a shortcut in the training data, it shows up in your test data as well. And it kind of does not represent real world usage. This is one of the fundamental problems where a lot of these issues come up. But there's also sort of a bigger fundamental issue with leaderboards, which is that they essentially compute a single number and summarize everything with a single number, and a bigger number is better and lower number is worse. But that's really, really insufficient, because that single number by itself doesn't mean much. It's more about the difficulty of the data rather than the model. But something that we're going to focus on a lot in this talk is that it does not break down the model capabilities. It does not tell us what the model is good at. It does not tell us what the model is bad at. How can we improve the model? None of this stuff. Right? And so if we go back to this question of figuring out, does a model really work? Should I replace my model with this new thing? Should I use this new thing in our products? We know that relying on leaderboards and accuracy is not the right answer. And in other words, that this very fundamental problem, very common problem, is not actually a solved problem. We don't really know how to evaluate these models. And so in this talk, I'm going to be talking about some line of research that we've been doing in thinking about what are the possible bugs. And some of these ideas will go beyond NLP, as we will see. And in some sense, I don't care whether we're going to be doing this automatically or manually. So we're going to be looking at approaches that do both versions. There are ones that try to automatically find bugs and sort of almost like in an adversarial way. But we also have ways to help you manually find bugs. Yeah. Behind all of the methods I'm going to talk about is this idea of perturbation-based testing, where you have your original data, and you're not going to rely just on the performance on the original data, but you're going to make some changes to it. Right? So you can think of some transformation that you're going to do to the original X and Y to form these X and prime and Y prime pairs. And this transformation is very specific, very designed. You're not just making random perturbations. This is a very sort of domain specific, NLP specific kind of transformation. And you're going to have these changes, and you're going to have some expected Y prime, right? So Y prime is like, hey, I've made a change such that Y should be different, so it's Y prime. And then you're just going to run X through the model, see what comes out of the model, see if these two things match or not. This is a very high level description. We're going to cover a bunch of things within this sort of bigger umbrella. We're going to cover a bunch of automated techniques. I'm going to cover two, but there are a bunch of other ones as well, where you automatically try to find the transformations, essentially, or the transformation function that gives you mismatches. That's what seers and triggers does. And then you can also think about manually creating transformation functions just to create robust evaluation benchmarks. Right? And then there's a bunch of work we've done. I'm going to only talk about one of them. And for the most part, I'm going to cover the rest of them very quickly and focus on checklist, which was our paper last year on how to test NLP models. Okay, so first I'm going to start with this work led by Eric Wallace called Triggers, where the idea was we wanted to learn a transformation function that identifies an X. So we're going to concatenate an irrelevant phrase to X, and we expect the output not to change, but we're going to find the phrase that actually causes the model prediction to change a lot. All right, so Y prime is we expect it to be the same as Y, and so that's what it's going to look like. I have to warn you that we were trying to find the phrase that can make the model misbehave as much as possible. And so that means that this is going to have some strong language. We wanted to find the worst possible bug, so to say. Okay. So in this work, here's kind of what happens with these triggers. These triggers are these short phrases that don't mean anything. So you can see the trigger here is zoning, tapping, fairness. It doesn't really mean much. And you have a bunch of inputs here that are all positive reviews. You know, movie's amazing, give him the Oscar, worth every minute, and so on. And the model is correct on them. The model predicts positive for each of these movies. But when you add this trigger as a prefix to these negative, you can see positive going to negative. In fact, the accuracy of the model being as high as 86%, drops to 29% because almost all of the positive reviews become negative. It's just one example, but this is what it is. Here's a slightly scarier example. This is for question answering. This is a pretty accurate model, pretty state-of-the-art. The question was, why did he walk? And you have a paragraph here for exercise, Tesla walked between blah, blah, blah. And you can say, well, the answer is for exercise, right? Or exercise. And the model gets it right. You can see exercise here. The second question is about why did the university see a drop in applicants? There's a whole paragraph here, and you can see crime and poverty is the reason you see a drop in applicants. Now, the way triggers work here is you want to control the output, or the adversary wants to control the output. So the adversary wants to put a different answer into the output. In fact, they may have a specific phrase that they always want to put in the output. So the trigger looks like this, where you have why, how, because as part of the trigger. That's what we find automatically. And then this underlying part, to kill American people, is a phrase that the adversary picks. You can pick whatever you want to, and that becomes the answer. So you can see model, why did he go for a walk? To kill American people. What is scary about these triggers is you can use the same phrase and the same answer on every kind of question. So you can take it another context here, and you can put exactly the same phrase here, and the answer in this case will also become to kill American people. Somehow this trigger is making the model ignore everything, ignore the question, ignore the context. In fact, as high as a third of the answers become to kill American people. So we're able to get the model by adding this phrase to behave in this really undesirable manner. Okay. That was a quick run through the first piece of work. Now I'm going to talk about Seers. In this case, what we were interested in was making edits that keep the meaning the same. So again, we're taking X, we're doing some transformation, and this transformation is going to change a bunch of things, but it's going to keep the meaning the same. That's the main goal. Okay. And again, in this case also, we expect Y prime to be same as Y, because the model hasn't actually changed. Right? The input instance hasn't actually changed. You've just rephrased things. So an example of Seers is exactly what I showed you earlier. You have what type of road sign is shown. It says stop. You replace what with which, and it says do not enter. Now, very different from triggers, this is one where you could argue that this is an actual bug, and it is very likely in the real world. But this single example doesn't really tell you how likely it is. It just tells you that this happens for one instance. Is there a way to take this idea and generalize it? Does this happen for every question? Does it happen for certain styles of questions? Does it only edit? And so with the Seer stuff, we tried to characterize the scope of each of these edits by using some rules. And by rules, you should think of it as like regular expressions almost, or simple replacement rules. If you see this, then replace this, right? So for example, we would say things like, every time a question starts with what type, any question that starts with what type, if you replace it with which type, there are two things that happen. First, the meaning does not change when you replace what type with which type. This is sort of an automatic assumption that comes out of the model. And the second one is that the model changes its prediction a lot of times. And those are the sort of two things we're looking for. A different rule might be at an even higher level, where you can say, I'm not just going to focus on type, I'm also going to include just nouns. So if there is what noun, and I replace it with which, the same noun, the model changes quite a bit, but the meaning should not change. And in fact, that turns out to be the right rule, the right in the sense that it's the most broad one. It covers a bunch of questions, many more than what type. but also the probability that model changes its prediction is still pretty high. So here are some examples. I'll quickly go through some for sentiment analysis, which are movie reviews, and show you what some of these rules look like. These are very simple rules, but very surprising rules because they tend to affect the model. So here's the first rule. Movie is getting replaced by film. So what does this rule mean? This rule means that when movie is replaced by film, the model changes its prediction, even though it should not, because the review hasn't changed just because you replace movie with film. In fact, in this case, you can see the review. Yeah, the movie pretty much sucked. That's a negative review. You replace movie with film, it becomes a positive review according to the model. This is not movie making is negative, but this is not filmmaking is positive. Doesn't make sense. The model also gets affected by replacement in the different direction. So you can take film, replace with movie, and so you can have a review that's excellent film, that's positive, but you replace film with movie and it becomes negative. Okay. And there are a bunch of other rules that I encourage you to look at papers and look at it. Right? But these are what I would say are actual bugs in the model, and we have automatically found those. There was no manual intervention here. You just let the system run on the data set and it finds all of these examples. Okay. I quickly want to give you one last example before I talk about checklist, which is this example of slightly higher level intuitions of these transformations. In this case, we're going to be talking about implications. This applies only to question answering, so we're going to focus on that. And the transformation here is going to be to change the question such that you know what the answer should be. This is pretty vague. I'm going to give you an example and it'll become pretty clear. So let's look at this example. This is the visual question answering. You have an image here and you can ask, how many birds are there? That's your X. Your Y is clearly in this, the Y is 1. Okay. How many birds? 1. Now, given this question answer, there are a couple of other things that get logically implied, like deterministically implied. For example, if I say, is there one bird? I'm sure all of you will agree. Well, if you have said how many birds, 1, then is there one bird has to be yes. Are there 2 birds? Well, no, because you said there were only 1 bird. And are there any birds? The answer would again be yes, right? Because you said how many birds? 1. In fact, these are such strong logical implications that you don't even need to look at the image to come up with these systems. These are question answer pairs, right? Conditioned on the fact that the model says how many birds is 1, the answer to all of these other questions should be deterministic. When you actually run the model gets the first answer correct. It says there is only 1 bird. Or if you say how many birds, it says 1. But for all of the other questions, it gets it wrong. Is there 1 bird? No. Are there 2 birds? Yes. Are there any birds? No. There's just no consistency in the model predictions. And so what we did in this paper is to create a huge data set for pretty much the biggest question answering data sets at the time, BQA and Squad. One was visual, one was sort of based on context, and automatically created these logical implications and tested the models at the time and showed that those models were not very good. Yeah. All right. So with that, I'd like to spend the rest of the time talking about checklist, which is the work we did last year. And the goal was to sort of bring together all of these ideas under a similar kind of framework. So the main goal here with checklist was to come up with a framework to help brainstorm and generate comprehensive tests for an NLP model for a given task. Right? Why did we want to do this? Well, at the time, there were a bunch of known issues that NLP models just faced, and many of those still are as a problem. There are lots of shortcuts shortcuts. There is a lack of fairness, and there is a lot of bias against specific people. There's a lack of consistency in the output. It's not robust to typos, things like that, right? And you've seen a bunch of examples of these, maybe all of these in this talk already. But the way people were approaching this was they would look at the specific issue in a specific task, right? So somebody would say shortcuts in machine translation, or not robustness to typos in question answering, or lack of consistency in NLI, right? And you can sort of do these pairwise things, and you can find papers out there, including our own. I'm not saying this is other people. But the tricky thing is, if you think about a user, the user has their own model and has their own task. And it's not clear from a point of the user for their model and their task, which of these is relevant. Like, are there shortcuts and biases on their own task? Like, there doesn't seem to be a clear way to know that. Are there other issues that are not one of these known ones that are kind of unique to the task that the user is looking at? Is there any way for the user to just evaluate the model, right? So we're going back to the main question. And one thing sort of that struck us was like, oh, if only we had experience testing complex systems. And turns out that outside of machine learning, this is a very common problem. People are thinking about testing complex systems, whether there are rockets or database systems or, you know, finance industry. Like, everybody's thinking about testing complex systems, specifically in software engineering. So are there lessons that we can use from software engineering to do testing better for NLP? Okay. So what I'm going to do is I'm going to outline some of the lessons from software engineering and how we can apply them to test NLP stuff. Some of these lessons will be common to you. Some of this, depending on how familiar you are, might be new to you. But their application to machine learning and to NLP is still kind of not quite there yet. So the first principle is to test small units, right? Create unit tests, test the small capabilities of your software. We don't really do this. And just to be clear, what I mean by small units is not like neurons or activations or attentions or anything like that. Those could be considered units inside the model. Instead, for NLP models, I'm talking about sort of the fundamental linguistic capabilities. Like, what do you expect the model to be able to do if you wanted to succeed on a task? And we'll see examples of this, but things like, can it handle negations? I should be able to write a unit test that just tests negations, or coreference, or lexical variability, and so on. Right? The second principle we looked at was whether we can decouple the test from the implementation itself. This is also really important, and actually for machine learning, it makes a lot of sense. You don't want to care about what the model architecture was, what the activations was, what's happening inside the network, the training loss, the optimization, none of that. If you're saying a model is able to do the task, you should be able to test just that functionality. So in machine learning or in NLP, what that means is you focus only on the test time prediction of the black box. Like, explicitly treat the model as a complete black box, and you should be able to test whether it's able to do something or not. And the third thing we took from software engineering were the kinds of tests that we could use. The first ones were simple unit tests, where instead of just thinking of it as accuracy, what we were going to create were the set of minimal instances that are trying to test for a single capability. They're very simple, almost like sanity checks, but they're testing for a single capability. The second type of test that we're going to use is mutation testing, where we're going to take instances and change it somehow and see if the output changes or not with some expectation. And this is, of course, the stuff that I've been covering earlier in the talk so far. Yeah. So I'll give you an example, and then we'll see if we have time to go for a different example. But let me give you this example first. So what we're going to do first is we're going to do sentiment analysis. So put yourself in the role of someone who needs a sentiment analysis system. You've been hired as the new machine learning engineer, and your bosses are telling you to create a sentiment analysis system. And also assume you're like an airline company, and you are on task to go to Twitter, find all the tweets and classify that mention your airline and classify them as positive or negative. Right? Seems like a pretty practical use case. Turns out there's already existing models that companies sell. That is probably the one you should start with. So you would probably go with a big name like Google, and then that's the one that I'll give you an example of here. They have some model, you don't know what it does. You know that they publish papers and stuff, but there's some model that says that they can do sentiment analysis on social media. Okay, so now you want to test this system, right? Is it useful for what you want to do? The first thing you would do, or you should do, is to list the different capabilities that you think the model should have. If they're able to do the task, they should be able to handle these things. And we'll see examples of that. Then there are a bunch of tests that you have to make. So you're going to create sort of a matrix where you're going to put all of the tests as rows, or all of the types of tests as different columns, and the rows will be the different capabilities. Okay, I'll give you an example and it'll become much clearer. So let's look at the first kind of test that checklist introduces, which is minimal functionality test. You should think of it almost exactly as a unit test, where you're just creating simple instances that somehow are minimal in what they're trying to test. So we're creating a column for this minimal functionality test. And first, we are going to test whether the model is able to handle simple vocabulary that is required for sentiment analysis. Just like some words are positive, some words are negative, how good is the model in just handling that? So here's what we would do. We would write some simple instances like this was a great flight and expect it to be positive. I hate this airline, expect it to be negative. I like this seat, expect it to be positive, right? Create these bunch, send them to Google and see what the Google output is and just says pass or not. In some sense, this is accuracy over these just 3 instances. But the important thing is you've created these 3 instances just for a single capability. You just want to know whether the model understands great and hate and like, right? In fact, these 3 tests are not enough because these 3 tests are, they're very anecdotal. So checklist has a way of generating hundreds or thousands of examples that follow the same structure. Very much like this was a great flight, but you'll create hundreds of examples of that. And then you can compute how good Google does or how good the sentiment classifier does on this whole set of test cases that are all measuring just a single thing. And turns out between positive and negative vocabulary, which looks like this, the model has a failure rate of 7%. So on something that's really, really simple, it should know what hate is bad, like is good, great is good. It still fails 7% of the time. That kind of sounds high to me, but again, depends on the use case. Right? Here's another example of a minimal functionality text. Maybe you care about neutral because a lot of people just say things on social media. Maybe they're not just having a sentiment towards your airlines. So you can create a bunch of neutral statements. You can just say declarative statements like, this was a commercial flight, or that was an English cabin crew, right? These are all handwritten examples. And you expect all of them to be neutral. And on these 2 examples, Google is wrong on one of them. And again, you can take these as structure. You can create hundreds and thousands of examples, and you can evaluate Google on all of them. And turns out 11% of the time, Google doesn't know that these declarative statements are neutral. And I'm not going to pick on Google. Let me just say the model that you're testing doesn't know 11% of the times that these statements are neutral. Right? So now it's not just about accuracy anymore. It's about specifically, how good the model is on neutral things, how good the model is on positive, negative, just with this simple structure. Right? But we go way beyond that. Here's another example of MFTs. These are unit tests, but we're going to target negation, right? So we're going to say something positive and put a not, or somehow negate the sentiment, and see how good is the model at detecting negation. So here are a few examples. The cabin crew was not good is clearly negative. The pilot wasn't nice is negative. The flight wasn't great is negative. And turns out Google only gets one of them right. The other one, especially if the flight wasn't great, Google thinks is actually a positive sentiment. And again, we generate hundreds and maybe thousands of these kind of examples which follow the same negation structure. And turns out the failure rate is as high as 50%. These are very easy negations. All we've done is like added not in some way. And the model fails 50% of the time to get the right sentiment. Okay. That's just a single type of test. There are other types of tests as well. The second type of test we're going to look at are invariance tests. These are tests where you take an instance and an actual instance. So in this case, you would take actual airlines tweets and you would change something about them, expecting the output not to change, and then see how many times does the output actually change. Okay. So we're going to be looking at named entities first. These are just entities, or these are words that refer to real locations or real people and things like that. Here's an example. These are two tweets. The first one says, at American Air, thank you, we got on a different flight to Chicago. And the second one says, at Virgin America, I can't lose my luggage, I'm moving to Brazil soon. Okay. And what we're doing is we're changing these locations to a different location. So we're saying, let's replace Chicago, and it's a US city, to another US city, which is Dallas. Let's change Brazil, which is a country, to another country like Turkey. And what we are expecting, because of sentiment analysis, we are expecting that the sentiment wouldn't change. If you are positive about your flight to Chicago, there's no reason changing it to Dallas should change your sentiment. Same with the second one. You're moving to Brazil soon. I can't lose my luggage. Whatever the sentiment is, it shouldn't change just because you're moving to Turkey. Right? And turns out in both of these cases, the model actually fails. It changes. First one goes from positive to neutral. The second one goes from neutral to negative. And in fact, you can run it over a large collection of instances where you take real tweets and you change it and you see what happened. And when you're changing locations, about 20% of the time, the model changes its prediction. Just to be clear, we're not like just looking at, hey, does the probability change or something like that? We are actually looking at, does the model completely change its prediction? Okay. As the last type of test, we're going to talk about directional expectation test. These are tests where we are going to change the input again, as we've been doing, but have a certain expectation about the output to change. So I'll give you an example for the vocabulary, which we were trying to test whether the model knows positive and negative words and so on. And again, for directional, same as invariance, we are going to take actual tweets and we're going to change them somehow. The test that we did in this case was to take actual tweets, like at American Air, service wasn't great, and we added a negative phrase to it. You are lame. We added it to the tweet. In the second case, at JetBlue, why won't you help them? Ugh. We added, I dread you, right? And the idea here is we are adding a negative phrase. There is no reason the sentiment should become more positive. If the sentiment becomes more positive when you add a negative phrase, you have failed the test. Right? And turns out, so the expectation here is for the sentiment to go down, or at least not to go up, right? When you look at this down arrow, you should think like it should not go up. And turns out in both of these cases, the model fails. And in fact, overall, almost like more than a third of the time, when you add a negative phrase, the model thinks the instance is more positive. Okay. All right. So what have we actually done with this checklist? These examples are fun to look at. It's always fun to show that these companies or these research models and the state-of-the-art stuff is broken, but what is sort of the actionable stuff here? What checklist provides is a paradigm and a tool to easily generate tests. What do you have to do? The first step of checklist is to look at your task, spend some time understanding what are the capabilities needed by the task. What are the different behaviors you expect it to have, right? If you're doing sentiment analysis, oh, it should know what's a positive word, what's a negative word. It should know negation. It should not care about locations, things like that, right? Then you should just write test cases for each of these capabilities, right? This is not specific to a model. You're just writing test cases and think about like different ways of defining this behavior and trying to write tests for it. Use labeled, unlabeled, synthetic examples, whatever you have in order to write these. And then the third step is the easiest one. Just run your model and you'll get a number. So you get a model is good at, what the model is bad at. Yeah. Checklist also provides a bunch of tooling. I'm going to go quickly over what these do. We have a way to write templates. So you can start with a sentence like, this is a good book, and easily write a template manually that sort of takes that, this is a good book, and generates a bunch of other examples that have similar structure that should have the same sentiment, for example. We can also do things like automatically generate options. So we can say this is a good book and say, okay, what else can I put instead of good? And you can use BERT, which is sort of a state-of-the-art NLP model that will give you a bunch of choices that could go in there and make sense. And you can pick which of the ones you want to put to use to create test cases versus ones you don't. And there's a nice UI to be able to do this. You can also expand templates using lexicons. So we have lexicons of first names and last names, sort of differentiated by where they're from and race and sex and things like that. We have list of countries and nationalities and split by income and things like that. So you want to say things like, if I take a developing country and replace it with a developed country, does the sentiment change? Things like that. And same with US cities and religions and sexuality and adjectives, both for religions and sexuality and so on. Okay. We also use lexicons. We also combine BERT with WordNet. I'm not going to go into this too much, but there are clever ways to sort of figure out what are the right antonyms to replace as well. And doing it in a simpler way doesn't actually work. There are lots of perturbation functions like part of speech tags, contractions, rule-based heuristics, and so on. A lot of statistical expectation functions and things like that you might want to use when you're creating tests. Okay. All right. We also did some experiments to sort of show how well this kind of works. Give me a second here. Yeah, sorry, give me a second. Yeah, we ran 2 user studies, one with Microsoft people and one with some researchers. And essentially at Microsoft, they have a model that's very well tested. And they have their own benchmarks and things like that. They really care about sentiment analysis, so they have those people. And with question answering, we got some NLP researchers to sort of use this toolkit. And I guess to sort of let you know what the conclusions were, both groups felt that they tested capabilities better with checklists. They even tested new capabilities that they hadn't thought about before, even though they had been testing these things for a long time. And they found many new bugs. Okay. So just to wrap up my talk, I think we talked a lot about behavioral testing, perturbing and testing for a specific phenomena that seems really, really powerful. We talked about a bunch of automatic ways of doing this, bunch of manually defined ways of doing this, and you can look at the papers to learn more. And then we added with this checklist, which kind of tries to unify all this by providing a general framework and sort of a recipe on how to do testing for NLP. One thing I will do as the final takeaway slide is to encourage all of you to think about testing and making it as part of your pipeline. irrespective of what task you're doing. We've been talking to a few different NLP teams in machine translation, language models, and all of these tasks that we hadn't thought about. And for all of these conversations, the way they've gone has been an initial skepticism whether this stuff will even work, and maybe we were lucky in getting our tests or whatever it is. But people try it out, somehow get over the skepticism, try out. They usually are surprised by how problematic their model is, and then they tend to adopt checklist as part of their development. And if you are in the blue square right now, I would encourage you to at least try out some of these ideas, if not the tool itself, and hopefully surprise yourself and make your system better. With that, I'll thank you. I think I was a little bit over time. I apologize for that, but I'm happy to take a few questions if you still have time.
Yeah. Thanks, Samir. So it was very great talk. Actually, we have several questions, but unfortunately, we can take only one question. So maybe I can post one question, and the question is the following: that is there any notion?
And I can answer the other ones by typing them out. So
sure, that would be great. Yeah. So the question is the following: is there any notion of coverage of these tests that can be developed?
That is a really good question, actually. I think it's very, very difficult to do that, right? So the way that would be kind of nice if these tests were somehow comprehensive, but language is so difficult to sort of imagine what the space of language looks like, what somebody might ask. It's very difficult to determine. So yeah, in short, I don't have a good answer for that. What I would say is that these tests are designed to be red flags for your model. So just because a test passes, you shouldn't be like, hey, my model is perfect. The tests are designed to be more like, hey, if the test fails, you know it's a problem. If the test passes, you may not. And that exactly goes to the problem of comprehensiveness or coverage or any of these things. Yeah, it's kind of difficult, but diversity of tests is something definitely we are working on. Yeah. And maybe with models like GPT-3 and things, some of those things might be easier.
Yeah. Okay. Thanks, Samir, and thanks for accepting our invitation. Yeah, thank you very much.
Can I ask a question?
Yes, sure. Yeah.
Hi, Samir. This is Animesh here. So it was a fantastic talk. So I really enjoyed it from end to end. So as they say in modern day NLP. So I had one question, like the slide where you were showing these triggers about replacing film with I think it was like excellent film and excellent movie. So this kind of replacements. Yep. So I was just wondering, like whether the model in some sense was assuming that the phrase excellent movie is kind of a sarcasm. And that's why the prediction went the other way around. So I'm not sure.
That's a good possible hypothesis. It's not clear to me in that specific case. And it's also very difficult to know whether the model is doing it because of sarcasm or what it is, right? Especially if it's like it replaced credit to sarcasm. But yeah, it's possible something like that is happening. So when you're designing these tests, I guess you have to be careful about, would you call excellent movie a sarcastic statement? And I guess film and movie are so close to each other in my head that I don't really. It would have to be a little bit more explicit. Maybe the one with this is not movie making could be, this is not filmmaking, could be construed as sarcasm. I'm not sure.
Yeah,
but
sure.
Yeah.
So I was just wondering, like in the set of checklists that you developed, like these kind of test particles, if those could be also like a future interesting direction, like testing some sort of presence of simile, sarcasm, metaphors, and things like that. I was just wondering, like, if there is a scope for that.
I think that would be a great idea, and I guess whatever I've been playing around with these models, I expect them to fail horribly on those kind of tests. they tend to be really bad at sarcasm, at similes and metaphors and stuff like that. But it'll be fun to show for specific tasks. Yeah.
Thank you very much. Thanks, Samir, for attending the session and giving us like this great talk. Thank you.
Yeah, thank you for the invitation.
Yeah, thanks, Samir. Thank you.